looking at a data set using which we have built a multiple linear regression model. We did this in stages. We looked at simple linear regression models and numerical variables. We expanded that to multiple linear regression models with numerical variables. And then we incorporated categorical variables into a unified multiple linear regression model. And in the process, we ended up building a number of models. Which of these models is good? And is it true that the more complicated models are actually doing a lot better for me? To answer questions like this, we need to look at model performance evaluation. We need some way of understanding whether the model has learned adequately from the data. And we're going to review a few concepts of what learning means here, as in, if we are thinking of multiple linear regression as a method in machine learning, more particularly a method in supervised machine learning, then what does it mean for it to learn? And how can we translate the numbers that we see into how well it has learned? So in our model performance evaluation, we need to define these metrics like root mean square error, mean absolute error, etc. And for some of these measures, these are built-in functions and built-in calculations in scikit-learn. But for some of them, we will need to define our functions. So for those, here are some functions that have been defined. The first one that has been defined is my mean absolute percentage error, or MAPE, M-A-P-E. Just to remind you of what this is, take the error that is predicted and actual, take a percentage of it that is predicted and actual divided by actual, take an absolute value, and then average over the data set that we are using to calculate it on. So this is a function that's defined, and as you can see, it just does that. First, take the error, target minus prediction, take a percentage of it, divide by target, and then multiply by 100. Take the absolute value, which is a NumPy method, .abs, and then take the mean of all of it, with the NumPy method .mean. So this gives a function MAPE score, which takes as its input what is it that your prediction is and what are your actuals. We'll create a similar function for adjusted R-square, where what we do is we essentially compute the R-square. R-square is something that is there. In other words, scikit-learn allows an R-square to be calculated directly. It's there as a function. And we're modifying that with a formula that gets me to my adjusted R-square, which is here. So this formula, which captures how many variables are being put into this. And the last function that we are creating is essentially a table in which we are going to put all these criteria together, all the different metrics. Some of these metrics we just described, for example, the MAPE score function and the adjusted R-square function we just created above, and some are automatically there. For example, mean absolute error is already there, R-square is already there. And some, even if they're not there, we can easily compute through one line without necessarily defining a function. For example, mean squared error is there, and mean squared error, if I take the square root of that, I get root mean squared error. So that's a simple modification of a function already available to me. This is converted into a data frame. As I said, we need to get to a table which we can look at and say this is good and bad. And from it, it's going to report out all these metrics. So we're taking advantage of scikit-learn's own capabilities, and we're modifying it and occasionally writing our own functions to do this. Take your time to investigate how these functions are written, and it may be a good review of writing functions in Python as well. So now what we're going to do is we're going to take all our models and see what they look like for these scores. How are we going to do that? Remember that for all the models that we've built, we've actually given them names like linear regression 1, linear regression 2, let's just briefly review that. So if I go back to one of our models, any one of our models, you can see like linear regression 7. So linear underscore regression 7, we began with 1, ended up at 7. So we've named all of them. So those models with all the fitted coefficients and all of it now exist as objects for me. So I don't need to rebuild anything in order to do the comparison. I can use all those models that have already been built and keep running the same comparisons for all of them. So let's see how that works. So this model performance underscore regression is a function that was created here. In other words, something that was created here that summarizes and says, give me a model, give me a predictor, and give me a target. In other words, give me the predictions from the model and give me the variable to which I'm going to compare the prediction. In other words, prediction and target. In the notation of machine learning and statistics, y hat and y. And so now, for this model, use the model to get y hat and then compare it to y. And using this model performance function, get me my output for all my metrics. Now here we are. So if I run it for my first regression model, remember, was for sales versus advertising. And you can go back and review that at this point in time if you wish to investigate that model a little more. And so if I want to predict sales only as a function of advertising expenditure, this is the quality of performance that I get. So for example, my root mean squared error is 2753. Doesn't tell me much because I don't have something to compare it with. So if I want to compare it with, I can think of it as a standard deviation of something that's on the range of the variability of the entire sales, which is I think around 24,000 or something of that sort. You can do that. If you're uncomfortable by simply interpreting these numbers, don't worry, because we're not going to interpret these numbers directly. We are going to compare. But if you really want to interpret them, here are some interpretations. MAP is 9.64. It means that on an average, I'm about 9.64 percentage points away from sales. My absolute prediction error is a little less than 10%, 9.6%. I'm making that percentage error as that much of sales, 10% of sales is not being predicted by this model correctly. The other interpretation could be from R square, 0.41. What does this tell you? This tells you 41% of the variability in sales is explained by variability in advertising expenditure. That is the interpretation of R square. 41% of the variation in sales is explained by advertising. Conversely, or said differently, 9.6% is the approximate error that I'm away from sales if advertising is used. So these two you can use as general benchmarks. But let's see if they become better or worse as we do something else. I want to point out what I did this analysis for. And I should have pointed it out before. This was done with my original data, which was my training set. This whole explanation that I gave. This was done with my training set. 80% of my data. This training set was used to build my model. So my model performance here reflects the quality of my training set. It reflects the data that went into the analysis. But this isn't exactly what we want. What we want is an assessment of how well this model is going to work if it forecasts into the future, if it predicts on a new set of data. So now what I'm going to do is I'm going to look at the same performance measures, but this time from the holdout data set. So my actuals here will now be from my test data set, from the 20% of the data that I did not include in my model. Now, this in some way is a more honest test of forecastability or predictability of the model. The first analysis is good. It tells me how well I analyze my data. But this second line is better because it tells me how well I can do on a new data set. And when I run this, I get this answer. And now for a new data set, 38% of the variability of sales is explained by advertising. And the error that I'd expect to make on predicting sales, unseen sales from unseen advertising, is about 9.96. And this is typical. It's more than on the test set. When I am trying the model on data that it has already seen, the MAP is 9.64%. On new data, it is 9.96. This is what happens. The performance on the test set is a little worse than performance on the training set, but it's still comparable. It's still close. 9.96 is not that far above 9.64. 3.8, which is the variability in sales explained, is a little less on the new data than on the data on which the model is trained. But 38% or 38.5% is not that much less than 41%. What that means is that the model has generalized well. It has generalized well to newer data sets. Whether this MAP is large or small, I'm not answering. Whether this R-square is high or low, I'm not answering, not yet. But I am answering the question that is this model predicting well outside of the data set? And the answer is, without doing too much analysis, I would say not bad. It's not a very professional sounding answer, but these numbers are what you would typically see if the generalizability is good. A slight degradation in performance as you move from the training set to the test set. Remember, this model, what I'm calling LinReg 1, has not seen the test data. These numbers have not been used to build the model. So now that we've seen this, we can try this for different models. Let's say for the training set, what happens if I look at the simple linear regression with discount percentages? So if I look at discount percentages, and we know from the original plot of the data set that discount percentages is not that strong a relationship. It is positively related, but not as much. And that is reflected here. My R-square is only 6%, 0.06, far smaller than in my advertising case. My MAP is 12.46%, larger. And I can, if I now want to, use the other criteria. My root mean squared error, which was 2,753, is now 3,858. Every criteria is worse. RMSE is larger, MAE is larger, MAPE is larger, R-square is lower, adjusted R-square is lower. I'm not talking too much about adjusted R-square here because adjusted R-square only makes sense if there are many variables to look at. So just by looking at this, I know that as a simple linear regression, discount percentage is not as good as advertising. Advertising explains 41.5% of sales. Discount explains 6% of sales. And this is on the training set. What about on the test set? On the test set, again, the model, R-square goes, in fact, slightly up here. My MAP goes up here. These are not particularly good models, but again, I'm seeing comparable performance. My MAP has going up by not as much. It's not a good model, but it is still generalizing well. It means it's not capable of picking up a good relationship. Why not? Because sales actually does not depend only on discount percentages. There's only so much the model can do. But for the training set, what it has picked up, it is perfectly capable of using that same model, good or bad, on the test set itself. So, but this is not a model that I would be inclined to go forward with. An R-square of 6% typically doesn't cut it, and I already have a better model. What about price? So if I do this with price, and price is interesting because price had a negative correlation, but its R-square is 2%. It's not a very good predictor, despite the fact that the plots seem to suggest a reasonable negative correlation. But the correlation was about minus 0.16, if you remember. For advertising, it was much larger, 0.6 something, in the range of 0.6. So a greater positive correlation gave a greater R square. A lower negative correlation gave a lower R square, which is 2%. My RMSE on the training set is 3,558, which again is a lot less. So the model on price is also not particularly good. And in the test set, I'm seeing a very similar performance. My RMSE is still correspondingly high. My R square is still correspondingly low. By the way, I'm focusing on these. In turn, I could also have spoken about MAP, which is at about 12%, 13%, etc. So you get a ballpark figure of how good linear regression is. Linear regression is capable of getting to within about 10% of the actual sales, at least with the variables we're looking at. When you build many models, you get a feel for how well these models can work in practice. Now we're going to keep doing this, and we're going to keep doing this with more and more models. Now we're making our models richer. Multiple linear regression with 3 continuous variables. We now have sales, advertising expenditure, and discount percentages. So if I run this, I get an R square again of 41%, a little more than before, because advertising is in this model. My RMSE has again come down to 2753. On the test set, my R square has gone down as expected. My RMSE has gone up as expected. It is generalizing, not badly, but there is some degradation in performance when I want to use my model to predict outside. Most machine learning folks tend to compare models by looking at something like RMSE or MAP on the test set only, because that's the fair comparison when you are on that objective of linear regression. Which objective? The objective of predicting or forecasting. Because their performance on the test set is what you really want. You're not so interested in the coefficient. You're not so interested in interpreting what each coefficient means. But you are interested in being able to predict for a new data point. Building up the model, if we go now towards something that includes more and more variables, say including price as well, including popularity. What was special about popularity? It was a categorical variable. Did that categorical variable, which gave about a 500 lift in sales as it jumped from one level to another, make a difference? Let's see. Let's run it on that model. This is sales versus advertising, discount percentage, product price, and this categorical variable, which was converted from 1 to 5. If I run this model, I get an R square now of 66%. 66% on the training set, much larger than my 41% and my 42% that I've seen before. Now I have a significantly better model. My RMSE is 2000. Again, smaller than the 2,500, 2,700 kind of numbers that I'm seeing. So now I have a significant jump. So I had a jump when I included advertising. It took me to 40 and above. Now, when I include popularity, it's taken me to 66 and above. My RMSE is now almost down to 2,000. Much smaller than the 2,700 or so that advertising gave, and even smaller than, of course, than discount percentage and product price, which gave me around 3,000. So I'm improving my model. It is still generalizable. It's still generalizable if I run this again. Yes. If anything, and this is a little awkward, my RMSE is lower on the test set than in the training set. Doesn't happen often. Can happen. Mathematically, there's nothing that says that the test set performance has to be worse than the training set performance. They are randomly chosen. It's usually the case that test performance is worse. But it could be the case that test performance is in fact better. That is indicated by RMSE. On R square, my performance is slightly degraded. Actually, it's increased as well here. R square has gone up on the test case. Here, for this model, there is strong evidence that it generalizes well. But again, Just to remind you, this is an abnormal state of affairs. In most machine learning cases, the test set performance will be worse than the training set performance, as we have seen before. It's only if the randomization turns out to be in some way accidentally good for the test set. In other words, the test set is lying closer to the model than the training set is. Unseen data is fit better than the seen data, that this happens. But it may happen, but it's rare. So when it does, you are now more confident about generalizability. To end this exercise, let's take a look at what happens if I put everything in it. Linear regression 7, all the variables, numerical, continuous, discrete, categorical, one-hot encoded, everything, all the variables put in. And we have seen that equation. That equation now on the training set has an R-square of about 71%. Close to 71%. 71%, the data says itself, 71% of the variable in sales is explained by all the other variables in the model. If I want to use it in prediction terms, I would expect to see about 6.8% error in my sales prediction. My root mean square error is now less than 2000. On the test set, what is happening? On the test set, I'm now seeing my R-square to be about 72%, 73%. My RMSE is even lower. This model is generalizing well, and it is explaining to about 70%. For a pure business application, that is a commercial kind of data set in which human behavior plays a role, like sales and the willingness to buy, 70% is an acceptable R-square. Many commercially used models are at that level. Human behavior is not very predictable. And if you can explain 70% of sales by a bunch of variables where human variability is inherent within it, that's not something to be necessarily ignored. Another point, as I said, is that you have about less than 7% error that you're expecting to make in your sales prediction. In this case, when all other variables are looked at, you will see something that adjusted R-square is slightly less than R-square, because remember there are many variables here, 11 variables, including the increase due to dummy variables. And therefore, adjusted R-square is going to be in some way perceptibly smaller than R-square. But again, since we're not comparing large models, that's not going to be very visible as a metric here. I've tended to ignore MAE, mean absolute error, but this entire discussion you can now review and think of it by staring at the mean absolute error as well. So now what we can do, of course, is compare all these models and see what happens, and then make an overall decision as to this is what we should be using.